Hello everyone, I hope you're all doing well. In this video, we will talk about data structures in C. A data structure is a specialized, organized way of storing, managing, and arranging data on a computer so that it can be used efficiently. Think of it like this. Data is raw information, like a single number, a letter, or a person's name. A data type like int, char, or float defines the type of that single piece of data. A data structure is a collection of those data elements organized under one name with a specific rule set for how they relate to each other. It's the blueprint for organizing data. The right data structure allows you to perform operations like insertion, deletion, searching, and sorting in an optimal way. Why are data structures important? They are crucial for writing efficient algorithms. For example, finding a name in an unsorted list or an array is slow. However, finding it in a dictionary or a hash table is incredibly fast. They help in allocating and managing memory efficiently. They provide a clear way to represent real-world data models, for example, a family tree, a network of friends, or a waiting line. Well-defined data structures are reusable components across different programs. C is a powerful language for implementing data structures because it provides direct control over memory through pointers and structures, or struct. Here are the most common ones, from basic to advanced: array, struct or structure, linked list, stack, queue, tree, hash table or dictionary, and trie. Array, the simplest data structure, a collection of elements, values or variables identified by an array index. All elements are of the same type and stored in a contiguous memory. Pros: fast, random access. Cons: fixed size, insertion and deletions in the middle are expensive because it requires shifting elements. Struct or structure, a user-defined data type that groups together related variables of different types under a single name. It is the fundamental building block for creating more complex data structures. Linked list, a linear collection of nodes where each node contains data and a pointer to the next node in the sequence. It is a dynamic data structure, which means that you can change the size at runtime. Linked lists are divided into three types: singly linked list, doubly linked list, and circular linked list. Pros: dynamic size, efficient insertions and deletions. Cons: no random access, uses extra memory for pointers. Stack, a last in, first out list, or a LIFO list. Think of a stack of plates. You can only take the top plate. The last element added is the first one to be removed. Key operations related to stack: push, add an element to the top. Pop, remove that element from the top. Queue, a first in, first out list, or a FIFO list. Think of a line at a store. The first person in is the first one served. Key operations: enqueue, add an element to the rear. Dequeue, remove an element from the front. Both stacks and queues can be implemented using an array or a linked list. Tree. A hierarchical data structure consisting of nodes, with a single root node at the top and child nodes below. The most common type is the binary tree, where each node has at most two children, left and right. Use cases: file systems, organization charts, and most famously BST or binary search trees for fast searching, insertion, and deletion. Hash table. A data structure that implements an associative array mapping keys to values. It uses a hash function to compute an index into an array of buckets or slots. Pros: extremely fast average case time complexity for search, insert, and delete operations, ideally on order of 1. Cons: can have collisions, which means two keys hashing to the same index. We can solve collisions by chaining. Hash tables are mostly used in implementing dictionaries and database indexing. Trie, short for retrieval. A trie is a specialized tree-like data structure that is optimized for quick prefix-based searching and storage. The key idea of a trie is that instead of storing the entire string in a single node, like a binary search tree, the characters of the string are stored across nodes, and the path from the root to a node defines the prefix of the strings it contains. Each node contains an array, or other collection of pointers to its child nodes. Each path down the tree represents a potential word or key. Nodes are usually marked with a flag to signify that the path from the root to that node forms a complete word stored in that trie. Key operations and characteristics regarding tries. Insertion. Time complexity is OL, where L is the length of the word being inserted. Search. Time complexity is on order of L, making it very fast. Prefix search. One of the trie's greatest strengths, you can very quickly find all words that start with a given prefix by simply traversing to the node representing that prefix, and then recursively exploring all paths from that node. This is the basis for autocomplete features. Memory usage. The main trade-off. A simple trie can consume significant memory because each node may have many null pointers. This leads to variants like compact tries or radix trees that compress chains of nodes with single children. Common use cases of tries. Autocomplete / autosuggestion. The classic example. Search engines and IDEs use tries to quickly suggest completions as you type. Spell checkers and dictionary applications. Efficient for checking if a word exists in a dictionary. This was all for Introduction to C. We covered the main topics and fundamentals, and it is up to you to start working on projects and diving deep to the exciting world of computers and programming. Make sure to subscribe so you don't miss our upcoming lessons and videos. Have a nice time.